So 11.1 parametric equations. Big idea here is it allows us to look at a direction. It allows us to see where something is physically going if we have a third parameter of a t. We could even do parametric equations in the third dimension or not. We're looking at x's and y's, but we are graphing the x coordinate and the y coordinate, both with respect to time. Okay? That's the most common. It could be done in a different fashion, but for us, it's just going to be done with respect to time. So if we have this, in this example, like a particle in motion or something like that, we can see where it's actually headed based on each time along the curve. Most commonly, oops, I didn't mean to twist it the same way. We can write it as c of t, the coordinate, right, is x of t comma y of t. So you'll see that a lot. These are going to be functions, right, with respect to t. Sometimes after we have it graphed with respect to time, it'll resemble a common polynomial or common function that we've already known about, but now we're thinking about it from a different perspective. Okay. So it brings in this idea of direction. So the Khan Academy video, one of the first one or two that I posted, is just showing the typical picture of, well, something coming off a cliff. This one was a car. It doesn't usually have that happening. But there was a car that he drew, and then you could see the path of the actual car. Rather than just having a velocity curve or a position curve up there, you really do have it all coming together, and you can see exactly at this moment in time, this is the location, the height, and the distance away from the cliff. Oops. Okay, so something, as simple as this. Sketch the curve with parametric equations. It's good to do real quick just to make sure that we're fully understanding how to do these ones, because obviously it's going to tie into everything. So we are given the x and the y, both with respect to time. You're basically coming up with a table of values, but it has three columns. It has a t, an x, and a y. And then you still plot your x comma y on your coordinate plane. So t, x, y. It's flexible. Sometimes a interval is given that would make sense. Otherwise, you can just pick different t values to try and find the pattern. -2, 0, 2, and 4. Just going with those to see if we can find some symmetry. So if I plug -2 into x equaling 2t minus 4, then I would have 2 times -2 minus 4. I get a -8 there. And if I plug it into the y, 3 plus -2 squared, I'm going to have 3 plus 4, or 7. If I go down through this list, put in 0, I get -4 for the x, and I get 3 for the y. If I put in 2, I'm going to get a 0 and a 7. Okay, so there's some symmetry. And if I put in 4, I'm going to get 4 and 19. So plotting this, right, I can see where that vertex would be based on what I'm having. And I can also make the observation I do have a quadratic happening. I have a linear input and a quadratic or a second degree output still, right, in terms of my xy coordinate plane. So -4 and 3, I can call that roughly right there. Then to the left and to the right of that, I have -8 and I have 0, both happening at 7. And then I only had one other point, but obviously I have that mirror image happening over here at 19. So if we labeled this graph a little bit more carefully, we would then say when t equals -2 here, t equals 0 here. Nope, I labeled that wrong. Forgot because we didn't actually do that point. T equals -2 here, t equals 0, t equals 2, t equals 4. So you can see that the path is heading that way. Okay. All right, so obviously most basic form of this type of problem, but getting the understanding. Okay. This next one, example 2, also pretty basic, but it can be really helpful. So we can rewrite this parametric C of t equaling, for the x is 2t minus 4, and for the y is 3 plus t squared again. We can write it now as a true quadratic, as a parabola. So the first thing you would do is say, well, my x equals 2t minus 4. So if I can write this in terms of t, then I can just substitute that into my y, and I'm looking for that y equals equation ultimately. So t would then be equal to 1/2 x plus 2. If that's what my t is, put that into the y equals, and then you come up with your equation. So y is equal to 3 plus 1/2 x plus 2 squared. Sorry, what was on my cheeks? So what's that? 3/4 x squared, 2 x's, and 4 more. So my equation that we actually graphed on the previous example is simply 1/4 x squared plus 2x plus 7. Okay. The quadratic, fine, the graph resembles one another, but it doesn't quite give you that same information in terms of time elapsing, direction that something is headed in. So it gives us a lot more information when we have that third parameter. You got it, Simon. Example 3 is another very basic example that we saw back in, go back, you got it. So example 3 here, very similar to problems that we saw back in, I guess chapter 4, we were talking about maximums and things like that, the application of the derivative. So same idea here, if we're given this parametric, the x is 80t, the y is 200t minus 4.9t squared. Essentially, right, the x is talking about across the x-axis, and that typically would be our time for a problem like this, and our y is our height. So the bullet follows that trajectory until it hits the ground. T is in seconds and distance is in meters. So part A is saying, well, what's the bullet's height at time equals 5 seconds? So you still would just use the y coordinate there. You would plug in 5 to the 200 times t minus 4.9 t squared. And that comes out to be 877.5 meters. Okay. So nothing really different in this problem, just the way that it initially is presented. The second one, what's the max height? Well, you know, we approached that differently back in Algebra 2. We said, well, that's where the vertex is, and if we were in standard form, we said negative b over 2a, and then we plugged it back in. But it still was this approach of when does it occur, like that time, that x coordinate, and then where exactly is it? Same idea here, but the calculus approach that we had was, well, when's the velocity 0? Okay, it's at this time, then I plug it back in and I find the corresponding height. So same approach here. When is that derivative 0? But just of the y coordinate. So y prime of t equals 200 minus 9.8t. Set that equal to 0. Again, as if we're using, you know, this format with Galileo, it ends up being the negative b over 2a, just like it did back in Algebra 2. It's not a coincidence. Right? Pretty cool, right? Because of the power rule. So time.
Wait, how does time do the power?
Right? Well, because this is a quadratic, right? Over here. So the 200 is my b, the 4.9 is my a. When you do the derivative.
Oh, that's so cool, yeah.
Yeah. And then you solve that linear equation. It ends up being negative. Right here, it's about to be it. 200 over 9.8. Right? So there's our b over 2 times a. 20.41 seconds. So that's when it's going to occur. We take that, we plug it back into the y coordinate. So y of 20.41 comes out to be approximately 2,041 meters. So that went into that 200t minus 4.9 t squared. Okay? All right, going smoother than last chapter so far? Let's hope that it continues the whole chapter.
Last chapter was correct.
This is easier than Taylor series one.
Yeah, for sure. All right. It was a good sign that I prepped a little bit yesterday, but I could prep for both sections last period in an hour, and I felt pretty comfortable with it. So that was a great sign for all of us. All right. So parametrization, there it is, of a line. Proofs and things like that for all of this stuff are in the textbook. For our purposes, we will go back and use this. It's, what word do I want? It can be like ratio based, right? So depending on the R that we end up using, that then in fact changes the S on the Y equation. But we're saying that the line through point P of A comma B of slope M, right, can then be split up between the X and the Y. And that proof showing how it gets split up from a single line to an X and a Y coordinate essentially is just below it in the textbook. So if you see this box, then below it would be the proof of it. We're not going to do it here. And that's true for all T's. For any R and S, with R not being 0, and the M is equal to the S divided by the R. So that's where that ratio comes in. So you could kind of tweak things as needed. I'll show you that in the next example.
Wait, what is R again? R.
R is kind of like the slope on the X coordinate.
Okay.
The coefficient of the T, I'll just leave it at that.
So T is just a top, right?
T is still just the time, correct. We're basically taking one tangent line or one line equation and splitting it into an X of T and a Y of T from that line at a given point. The slope of the original line is the ratio of S over R. The second one says the line P and the line through points P and Q. So if you're given 2 points, has this parametrization. I said it wrong, but I'm done. X equals A plus T times the difference of C minus A. Right, the change in X. And B plus T times the change in Y.
So limited to
Kind of, right? Like this ratio of M equals S over R. M is your change in Y over change in X. So you're still, the S is there, it's still the change in Y up there. The R is over there, it's still the change in X over there. Similarly here, but now I have 2 different points. Okay? So it's the same idea happening. We're splitting the slope up. Maintaining the ratio, it has to, obviously, if it's going to equal M. Right?
Is it limited to like when both lines are linear? When both coordinates are linear?
Yeah, that would be true. You're
So-
taking a line and you're splitting it, so the result is still going to be linear.
So if like yeah, I get it.
Well,
So-
we're going to then apply this. It kind of will apply to other functions too, but it's still a linear idea. Yeah.
So this only works for a linear function.
Yes.
Got it. So how do you find R?
I'm afraid that I don't like that answer. Well, it'll be specific to the problem that's given. This is of a line, but it's going to, this idea will still connect it to other things that are not linear. I'm going to say it like that, okay? The application could follow through to something non-linear.
Seconds.
Yeah?
Okay, got it.
Sees?
Can you go back for what?
I sure can. Okay, so this example pertains to exactly that theorem. Find parametric equations for the line through the point 3 comma negative 1, and the slope is 4. Okay, so the easiest way would be, well, let's just choose our r to be 1, because then our slope is 4, right? So pick, that's not the word pick, r equal 1, then s equals 4. S is just, which is our m. That's the easiest way. Then it would just be x equals 3, which is our a, plus r t, which you just get t. And y would then be equal to b, which is our negative 1, plus st, or 4t. I don't have to do that. I could do something else. I could say or, right? It's the same relationship. I could say, well, what if r is 5? If r is 5, right, m was equal to s over r. Then s is 20. So I'm keeping that same ratio. I'm coming up with a different relationship. So here I could write it as C of t if I did the other format. Is equal to, my x would then be 3 plus 5t. My y would then be negative 1 plus 20t.
So you can pick any R.
Could. I could, for sure. So there's different applications here. This bottom equation 5 is going to tie into my next example, and that will tie into the parametrization of an ellipse. But this is another application of what we were just looking at. So x can equal a plus r cos theta, and y can equal b plus r sine theta. So our t changed, basically. Our t is now based on the cos and the sine there. Okay, so here, this next one is applied using that idea. So we want to verify that the ellipse with this equation is parametric. Why can't I say this word? Parametric. No, but now it's like a verb. Parametrized by. Sorry, so it's a tough one for me. All right. So the c of t is equal to a cos t, comma b sine t, where t is between negative pi and pi. And we then want to plot the case where a is 4 and b is 2. All right. Yes, Simon?
I was wondering if you could maybe try adjusting the screen a tiny bit backing off to the left of the thing. See the parentheses are. Not bad anybody else.
They're small. Okay, how about I read them? Because can you read everything else?
Yeah, I can read everything else.
Okay. So in the parentheses it says x over a and then y over b for the ellipse equation.
Thank you very much.
You are welcome. Right. So we're going to first show that equation of ellipse can be parametrized by this relationship. I don't know why it's so hard. So all that I'm doing here is replacing the x and the y with the a cos t and the b sine t. So I have a cos t over a squared plus b sine t over b squared. You know, we're looking to make sure that that's going to equal 1. So it first becomes the a over the a can just cancel out, right? So then we first get a cos squared t plus a sine squared t, which of course is 1. Right, so I just replaced the x over a, the y over b, with the a cos t and the b sine t. So we're good. So that's just that verify step. Then it's saying plot the case of 4, 2. So similar to the very first example, we need to come up with 3 columns to figure out how we're going to graph this thing. So it tells us that we're looking between negative pi and pi. Okay. So I'm going to go, and I'm going to just do 0 to pi, because then I can reflect it from there. Okay. So 0, pi over 6, pi over 3, pi over 2, getting most of them, 2 pi over 3, 5 pi over 6, and pi. Okay. And I'm putting them into the a cos t, b sine t, where a is now 4 and b is 2. So I'm going to replace in my table exactly that. So I have, for my x, I have 4 cosine of t, and for my y, I have 2 sine of t. Okay, so if I evaluate each of those at 0, I'm going to end up with 4, 0 at pi over 6 as I'm going around the unit circle, and then multiplying by 4, multiplying by 2, I'll have a 2 root 3 and a 1. Then I'll have the opposite of that essentially. I will have a 2 and just a root 3. At pi over 2, now I would have a 0.
I'm a little bit confused. How do you get 4 plus t?
Oh, because they're telling me to use this.
Okay.
Yeah, so in general this works, and I could kind of stretch it and elongate it any way that I want, and you'll see that we'll get an ellipse back out of it. The 2 pi 3, so now I am in the second quadrant, I would get a negative 2 for that, and a root 3. Then I would get a negative 2 root 3, and a 1, and then I would get a negative 4 and a 0. So, plotting this on the xy plane, and kind of thinking that direction, right, as I move around it, at time of 0 seconds, I'm at 4, 0. Then as I move around, at pi over 6, 2 root 3, 1. I didn't mean to write 1, pi over 6 there. And as I keep on moving around, not totally to scale there, this is a height of 2 only. Let me put my y coordinate in a different color. No, I didn't do a good job of scaling that one. So we would be moving around in that direction. And we have negative 4 going on here, 4, negative 2, positive 2 up there as we go around the unit circle, but we have this ellipse shape.
I saw that it's t is between negative pi and pi.
Yes, yes.
Ms. Rodriguez,
Yes.
can you go over one more time how you got?
So this example, I'm just going to talk about this one. it's showing that we have different parametrizations of the same curve, and we're going to describe the motion of it along each of the following paths. So C1 of t cubed comma t to the 6th, compared with C2 is t squared t to the 4th, compared with C3 is cos t squared t. The relationship between every single x and y here is y equals x squared. All of them fit the parabola, which is why you see y equals x squared for all three cases. But the difference is the first one, t cubed comma t to the 6th, that fits the same pattern as a regular y equals x squared in the sense that it goes from the input is odd for the first power technically, and then the output is squared, even. So therefore, positives and negatives end up going positives for a quadratic. So the entire quadratic is a perfect match for t cubed comma t to the 6th, because it follows that same behavior. The second one, they're both even, right? So your input is just the positives, therefore your output is just the positives. So we're only looking at the right side of the quadratic
I
there.
mean, the input can either be positive or negative.
But it comes-
The output can only be a positive because it's squared.
Yes.
Because it's an even
The
count.
output for the x though.
Yes.
Yes.
Yeah, and that's why it travels back down for.
Yes, yes,
T.
exactly. So both directions happen, but visually on the graph, you're only seeing the right-hand side. Yep. The last one, cos t compared with cos squared t, similar to here. Well, actually, it kind of combines all of them, really, because you do see both sides of the parabola happening, because it goes from an odd to an even in terms of exponents. Right? So we have negatives and positives going in, and positives coming back out. But we're stopping up there at 1, right? It's going back and forth between 1 and negative 1. Okay? Any questions on that? How you can have the same visual graph, but depending on how you set your parameters, it changes, right? The direction, the outputs of all those things.
So because it's cosine, it's only positive, whereas an even pi.
Well, I can still put in my negative t's can still go in negative pi, 3 pi, and I can still get out 0 to 1.
Yeah.
And then similarly, right, I can put in positives, or the evens and the odds as they're showing them there too. Right.
Okay.
Right, so I described that the wrong way. The odd ones, the negative pi, the pi, the 3 pi, etc., are going to come out over here on the left-hand side, the negative side, and then the even ones are going to come out on the right-hand side. Okay. This one's kind of similar in terms of just thinking about the symmetry, as it suggests, the evens versus the odds. Okay. And then saying then to label points corresponding to 0, plus or minus 1, plus or minus 2, plus or minus 2.5. So an observation about the x coordinate here, t squared plus 1, is that it's going to have symmetry across the x-axis because it's an even. Okay? So we will have that positive and the negative happening. Then in the book, and it does a good job explaining it, we're just running short on time now. If we take a look at the functions of the x of t and the y of t, in terms of functions of t, we could make observations that the y of t portion is going to be negative when t is between 0 and 2. Right? Because I could factor the t out, I would be left with the t squared minus 4, and I could see where those zeros would happen. Right? And then it would be positive greater than 2. Then, even the book has you just graphing t cubed minus 4t to see what that polynomial looks like. And then it has you merging, which you ultimately have to get to. So the observations can be helpful, but they're not like a must do. You really can always default to the table of values and have your t column, your x column, your y column. And that's what ultimately we will get our graph from. But they're suggesting that if you can make these observations and conclusions, you can save yourself a little bit of time. If you know that symmetry is going to happen, then you just graph half of it and then reflect it. And that's what the suggestion on this example is. So if I only look at the positives, because I know that the negatives will have the same reflected result, then I can say, well, if I plug in 0 to my x, I'm going to get 1. If I put in 2, oh, I'm sorry, if I put in 1, and then I'll get 2. If I put in 2, I'll get 5. If I put 2.5 in, you get 7.25. And if I do the same thing with my y's, 0 gives me 0 again. 1 gives me -3. 2 also gives me 0. And 2.5 gives me 5.625. Okay. So I am going to get 1, 0 when t is 0. Then I'm going to get 2, -3 when t is 1. Then I'm going to get 5, 0 when t is 2. And then when t is 2.5, I'm going to have 7.25 and like 5.6. That's a little bit off. Okay, so I start with that portion. Okay. And they're suggesting that if I put the negatives in front of here, right, like what will happen? Well, the x's aren't going to change, right? But the y's are going to change by their sign, and we're going to have that reflection. Okay? So then the reflection that they're saying, just to save time on, causes that. So the whole thing is the correct graph. The example here is just saying if you can make these observations, then you don't have to make a complete ordered pair because you can come up with, the reflection.
Can you get back a little? No, when I think this is kind of weird. So what is the point that is what is the critical point?
What are you saying right here?
Yeah. Well, what is the coordinate of that?
Well, let's do it. Let's just, instead of assuming that let's just,
Because I plotted out everything, I got something different.
-1, -2, -2.5. So if we put those in, we're still going to get 2 here. -2 cubed should be a -8. Plus an 8 should be, oh wait, I skipped over. What did I do? I'm sorry. I'm still on -1. -1 plus a 4 should be a -3 still. And -2 comes out as 5. And -2 cubed, -8 plus,
It's gonna be
Very positive,
3,
right?
positive 3.
I'm sorry, yes,
Oh,
that was
that's
a positive 3.
14, right?
Yes. I got ahead of myself. 5, 0, and then the other one will follow the same way as well. Whatever, I mean, it might be helpful to take that t out so then you can see it as this. So that shows it's just changing the sign. is negative 5.625. All right, so clearly I didn't even get to 11.2. What do you guys want me to do? Do you want me to teach it live on Wednesday, or do you want me to post a video with it so that we can stay exact? I mean, no matter what, we'll have through 11.4 done. You tell me.
I mean, I'd rather have it taught in class.
Taught in class.
Cause it's just, like, you
There's not as many examples in 11.2. They're formula based. It's arc length and speed. There's only 5 examples, so I do think I can do it in about 15 minutes of time, maybe 20 minutes of time on Wednesday, the beginning of class. And if that what that would mean is maybe I do 11.2 and 11.3 on Wednesday and save 11.4 for Friday, and we still finish the same chunk. I can adjust dates and whatever. It's all quarter 4 stuff. Is everybody okay with that? So I'm not going to post the video. Well, I suppose I could post 11.1 separately, and then I'll pick it up. I think I can do that. Okay? Good? All right. Awesome. So if you're at home, you may sign off. We only have a minute left. Have a great day. Heidi, I'll see you later. What did we say? 1:45? Okay, cool. I'll see you then. Yep.
When should we post the notes?
Sorry, I was wondering.
Later?
Hey, Simon.
I have actually
Still not sure if we're gonna read spelling next.
It'll change. It'll change. Don't worry about it. Definitely. I'll finalize, like, once I know all the grades are totally in, Canvas and everything is synced. I always go through, and that, without you even having to ask, would have been done, but I appreciate, it's fine.
Don't discuss it much at all.
You are very welcome.
Would you do like this?
You too. Nico, your question,
That seems like a waste of time a little bit.
when will it be due? Why don't we make the 11.1, 11.2, I'll change that to Wednesday. Right, and then the problem set, whatever, I'll just bump to Thursday. It doesn't matter too much to me. You guys are hyper organized, which is amazing. As am I, so I understand it. So Wednesday works, right, because then you could just submit the notes after class. Problem set, give you an extra day after you've seen 11.2 to get that in. What about the discussion? You guys can go. It was great to see all of you. I'll have.
It's gonna be day on Monday? Oh, yeah, it is gonna be, or Wednesday?
Yeah. Yeah. F periods got gypped. Because like Friday was an F day of reading day, tomorrow's an F day reading day, and then I only see F day, we only see it one more time this week. So E day made out big time.
Wait, so Wednesday is E day,
Yeah.
and then Thursday is
F day.
F day.
So I see you 3 times this week.
And then Friday is E day. Oh, yeah.
Nice.
And since tomorrow's a reading day, I don't think Friday has to technically be a reading day. I think we can, in our class it doesn't matter, nobody's questioning it, but I don't know.
Alright, okay.
Okay?
Thank you.
Yeah.
Like 18th of group retreat, or there's gonna get figured out at the meeting or later?
Yeah, later. I don't know. They're like, all the camps are saying no, they're not doing it. So we're like, so yeah, we have to figure that out.
Thank you.
Hopefully,
I just-
hopefully I'll have an better answer for the meeting.
I just want to it's really good to meet you in person.
Yeah,
And,
it's so nice.
yeah. I'm still catching up the works, and
Okay.
I'll do it. Do like as many as I can before the weekend comes, so that we can have the time to grade it during the weekend.
Perfect.
The due period is on Monday, right now.
Yeah. All right.
See ya.
Bye, Ricky. Okay. This one I'm gonna skip and just, it's just an explanation, actually the explanation is,
What about,
what did I do? Evan Mullen's asking, stop the recording. All right,
so just, can you go back to the, example 7?
yeah, sure can. Cool. So 11.2 obviously didn't happen. I'm gonna go back to example